Good afternoon, everyone. My name is Lucian, and I will be your Yabo Physics tutor for today. Okay, we are still continuing with sound waves, superposition, and standing waves, and this is our fourth session in this chapter. Now, today I'm going to continue from questions number 22 to 26, I think. And let me just see, no one on Teams yet. It's loading, but while that is busy, let me continue with the work. Okay, now on your screen there we have question number 22. Okay, question number 22. It asks the following. Let me just enlarge the question for myself. A clarinet behaves like a tube closed at one end if its length is 1 meter and the velocity of sound is 344 meters per second. What is its fundamental frequency in hertz? Okay, now we know that the fundamental frequency is equal to, or whenever you watch this, you should know that the fundamental frequency is equal to the velocity divided by 4 times the length of the tube. Okay, so the fundamental frequency of a tube closed at one end, this works only for a tube closed at one end. This formula only works for a tube closed at one end. The fundamental frequency is then equal to just open up the fundamental frequency is then equal to the velocity of sound in that air column inside the tube divided by 4 times the length of the tube. That will give you your fundamental frequency. Now, the velocity of air is been given to us as 344 meters per second. I think I can erase this part here. I just erase all. The fundamental frequency is equal to the speed of sound in the air inside a tube divided by 4 times the length. That's the fundamental frequency of a tube opened at one end. Now, the speed of sound has been given as 344 meters per second. We divide that by 4 times the length of the tube, which in this case is 1 meter. This gives us 344 divided by 4 meters. The meters will cancel, leaving us with per second, which is also a nice way of saying hertz. Now 344, let me show you on my calculator that 344 divided by 4 equal to 86, and it is in hertz or per second. Okay, that is our very first answer, hertz or per second. Now let's look, this is for question number 22. Let's continue to question number 23. Question 23 asks us, let's check first. 86, check. Okay. Question number 23. A harmonic longitudinal wave propagating down a tube filled with compressible gas has the form Sx of t is equal to Sm cosine kx minus Wt. its velocity can be obtained from. Okay, now this is the formula for the displacement of every element inside of that longitudinal wave inside the tube filled with compressible gas. Okay, now its velocity can be obtained from the following formula. Okay, velocity can be obtained from W, the angular omega, I should say, omega over the angular frequency over the angular wave number. Okay, so omega over k. Now how does this work? Okay, omega we know is 2 pi over t, right? And we know that the angular wave number is 2 pi over lambda. Okay, now from primary school math, we know that if we divide by a fraction, we flip it over and we multiply. That's lambda over 2 pi. The 2 pi's are going to cancel, leaving us with lambda over t, which we know is just the velocity. Okay, so W over k, or omega, I keep saying W, omega over k is speed. And we've shown that it is so. Omega over k is speed. Question 24 at least, I should say. Question number 24. Let's look at it. Question 24. An organ pipe open at both ends has a radius of 4 centimeters and a length of 6 meters. Okay, so an organ pipe, it's a big pipe with a radius of 4 centimeters, which means it has a diameter of 8 centimeters and it has a length of 6 meters. What is the frequency in hertz of the third harmonic? Now the third harmonic is also known as the second overtone. Okay, let's assume the velocity of sound is 344 meters per second. Now the fundamental frequency, what is the frequency of the third? To get the frequency of the third harmonic, we need to first find the fundamental frequency. Now the fundamental frequency of an organ pipe or a tube opened at both ends is equal to the speed divided by 2 times the length. That is the fundamental frequency of a pipe opened at both ends. Now the speed is 344. 2 times the length of this pipe is 6 meters. Now 2 times 6 is 12, so 344 divided by 12. Let's see what that is. 344 divided by 12. That gives us 28.67, or just 28.7 hertz. That's the fundamental frequency. Okay. Now that's F1. Okay, the fundamental frequency. Now F3 is equal to 3 times F1. That is equal to 3 times 28.7 hertz. That will be the frequency of the third harmonic. Okay. Now what is 3 times the answer that we just got? Let's multiply it by 3. Let's clear that all. 28.7 multiplied by 3 gives us 86.1. 86.1 hertz. That is the 86.1. Let me rather write it here. 86.1 hertz. That is the frequency of the third harmonic, or the second overtone. Okay, let's check 86. Yes, it is indeed correct. Okay, let's continue up to number 25. Question number 25. I think I may have accidentally changed. Okay, go back. No, I don't want that. Okay, let me just continue. Don't waste time. Okay, a stretched string. 24. We've done. 25. A stretched string is observed to vibrate in 3 equal segments when driven by a 480 Hertz oscillator. Okay, what is the fundamental frequency of vibration for the string? Now, the fundamental frequency, the frequency given to us is the third harmonic. It vibrates in 3 equal segments when it's driven by a 480 Hertz oscillator. So it's the third harmonic and it is equal to 480 Hertz, that frequency. Now, we know that F3 is equal to 3 times F1, the fundamental frequency, which means the fundamental frequency F1 is equal to the third harmonic divided by 3. And we have F3 as 480 Hertz divided by 3 will give you the fundamental frequency. Now 480 divided by 3, go on your calculator, 480 divided by 3 will give us 160. So 160 Hertz is the fundamental frequency of the stretched string. Okay, it is 160 Hertz. Question number 26. There are 2 ways of doing this one, but I'll just tell you the easiest way. A string is stretched and fixed at both ends. Okay, so a string is stretched and fixed at both ends. Just show you. Okay. A string is stretched and fixed at both ends. That is 200 centimeters apart. Now, if the density of the string is 0.015 grams per centimeter and its tension is 600 newtons, what is its wavelength of the first harmonic? Now, you don't need the others. You need the tension and the mass per unit length if you want to calculate its fundamental frequency. But we know that the fundamental frequency is the one with the fewest number of nodes. Okay, so it's the one with only 2 nodes. The fundamental frequency in this case only has 2 nodes, and they are each at the end of the string. So it's like this. The string is like that, and those are the 2 nodes at the ends of the string. So there are 2 nodes. And you can calculate that fundamental frequency easily enough. All you need is just to use this formula. The fundamental frequency, or any frequency for that matter, is equal to n over 2L, if I remember correctly, times the square root of the tension, okay, over the tension divided by the mass density. Okay, that is the frequency you can get for that's the formula for the frequency and all the other overtones going with it. Okay, that's how you would get the fundamental frequency. You would sub in 1, n as 1, n as 1 there, and you would get the fundamental frequency. Now, they don't want the fundamental frequency. They want the wavelength of the first harmonic. So the wavelength of the wavelength corresponding to the fundamental frequency. I just want to check something that I'm thinking about now. Don't worry what I'm doing now. Don't do this. I'm just checking something that I've got here. I actually worked out the fundamental frequency myself. Okay. That has got nothing to do with this question. Okay, so they want the wavelength of the first harmonic. Now we know, or you should know, that the wavelength, that if the string length is equal to L, now if this string has a length of L, that L must be equal to the wavelength divided by 2. Okay, and you can see that if that L is equal to the wavelength over 2, that means that the wavelength is equal to 2 times L. So if we multiply 2 times the length, which in this case is 200 centimeters, they're 200 centimeters apart, or 0.2 meters, you get that it is 0.4 meters. It's the wavelength, or 400 centimeters, which I think is where they asked the question in centimeters. So 400 centimeters. Let's check. Yes, it is indeed correct. That is 400 centimeters. And I think that is all the time, or that is all the questions we'll be doing today. Thank you for watching, and whenever you watch this, please go over everything I just did slowly and make sure that you understand where I got everything from. Since there is no one watching and no one asking questions, I assume people are understanding what is happening. Okay, so thank you for joining or watching this whenever you're watching this. Much appreciated, and I will see you next week for our last year of physics session for the semester.